Hi, in this video I'd like to go over an example of the Bernoulli equation, or how it's applied in different situations. The example that I'm showing here has fluid moving in this direction into a 1-foot diameter pipe, and it's going to be transitioning in both height, the z direction, as well as in the actual diameter of the pipe. It's a 1/2-foot diameter pipe here and a 1-foot diameter here. And we're given the mass flow rate, the volumetric mass flow rate, and we're being asked what is the height that determines the difference in these two static pressure tubes. Now we notice that this one here is a static pressure tube, whereas the other one is actually giving us the stagnation pressure in the flow. All right, so what I'm going to do is I'm going to go over here. All right, so we're going to come over here and look at an annotated portion of the figure. So we notice that we have an inlet and an outlet that defines the 1-foot diameter inlet and the 1/2-foot diameter outlet. We see that we have a streamline that connects 2 points, point A located directly below the static pressure tap and point B located at the entrance to the stagnation pressure tap. Over here I've defined some variables. L is the height of the water above for the static pressure tap, and L plus H is the height of the water in the stagnation pressure tap as measured from the zero datum. The value of H is what we're trying to determine in the problem, and I've also introduced another variable here called S, which is the distance measured from point B up to the top of its pressure tap. Okay, so what I'm going to do here is make a couple comments, and the first is that these variables L and S are what we can refer to as dummy variables. They're being used to clarify the geometry of the problem, but ideally they should cancel out at the end of the problem. All right, so what we're going to try to do here is figure out what we know and what we don't know. And the way we're going to do this is applying the two laws that we're working with right now: conservation of mass, also referred to as continuity, and the Bernoulli equation. So right away, we have enough information to determine some velocities because we have the total mass flow rate, volumetric flow rate rather, and we have information about the inlets. So if I apply our conservation of mass between the inlet and the outlet, we have A1 V1 equals A2 V2 equals Q. And in this particular case, we can solve for the velocity of the inlet, because that's we're going to want to know what the velocity of the fluid is at point A. We don't really need to know what the velocity of the fluid is at the outlet, because when we're thinking about point B on the streamline, it's a stagnation point, and that velocity is going to be 0. So we go ahead and we find out that the velocity at 1 is Q over A1, so 4 cubic feet per second, divided by the area at 1, which is pi over 4 times the diameter squared, which in this case is 1 foot squared. So we end up with a value for the velocity of 16 over pi feet per second. All right, the next thing we want to do is apply the Bernoulli equation between these 2 points, A and B. So what do we know? PA plus 1/2 rho VA squared plus rho GZA. Well, we've defined the location of A as being the zero datum of our hydrostatic potential, and we've just determined a value for V1, and we recognize that here V1 and VA are the same values. So that defines these two terms of the left-hand side of the equation, and PA is unknown. Now, on the right-hand side of the equation, it's a stagnation point, so VB equals 0, and ZB is 3 feet above our datum. Here's the datum, and here's the value of 3 feet. So that gets us rho g times 3 feet. Now, what we know is that PA is given by the static pressure tap, so its value is rho GL. Okay, what does that mean? It means that we know the fluid here, let's write this over here again, along the streamline, here's point A, and there's other streamlines moving with it. All of these have the same velocity of VA. But anything measuring it from this side is going to be a static pressure. So the static pressure tap is going to be the total height of this fluid plus this distance here. So from A all the way up to the top of that column, which we have defined in this particular instance as being the quantity L. So PA is rho GL, and PB can also be defined by the height of the static water column. PB is rho GS. Now, what do I mean by that? Well, again, let's erase some things here so that we're not getting too messy in terms of what's going on here. I just deleted my A. So PB, right, the pressure here is a stagnation pressure, but the stagnation pressure is what's being used to rise or cause this water column to rise up. So the value of the pressure at B is given by the hydrostatic pressure, rho GS, which is what we have written down here. Okay, so we take those two values and substitute rho GL in for PA and rho GS in for PB, and this is what we're left with. So rho GL plus 1/2 rho VA squared plus rho GS plus rho G times 3 feet. Now let's take a look at this term. So rho G is common among both of them. And here's my 3 feet, and here's my value of S. So we find out that 3 feet plus S is equal to this value L plus H. And I'm going to make use of that. So here's S plus 3 feet. It's equal to L plus H. Over here, we find out that the rho's cancel, and I'm left with GL plus 1/2 VA squared equals, here's my GL plus my GH, and the GL's cancel on both sides. So I find out that the H that I'm looking for equals VA squared over 2G, and working out the values works out to 4.03 feet. And of course, we can see that the two variables that I was looking at here, L and S, are indeed dummy variables, and they cancel out.